All right, good afternoon, everyone. Let's begin. So today we'll be talking about section 4.4, indeterminate forms and L'Hopital's rule. So this indeterminate forms and L'Hopital's rule uses ideas from limits. So we'll be quickly reviewing limits, and you have learned at the very beginning of this course, we spent a lot of time studying limits. We discussed limits at length. Now I'll just give you a quick review so that you can recall when we start applying limits in solving indeterminate forms and L'Hopital's rules related problems. So the limit answers the central question, and that question is, what are the y values approaching as the x values approaching a? So it has to approach a certain value from both ends, from the left and the right. So mathematically, we can write this as limit as x goes to a minus. What I mean by that is I'm approaching from the left, f of x equal L, and if I'm approaching that certain value from the right, I can denote it as ax approaching x goes to a plus f of x equal L. And when that happens, from the left and from the right, if we approach the same finite values, so same finite number, that's when we say that the limit of this function f of x is equal to L. So now the function value can be different from the limit value. So if I am walking toward this door, you can predict that I'm walking toward this door. It doesn't matter if I touch the door or not, right? So the function value is like exact value evaluated at that point, but the limit value is the prediction that I'm walking towards that door, or we're approaching to a certain number. That prediction is the limit. Now, apart from that certain number, limit, we can consider limit as x approaches infinity. It can be positive infinity or negative infinity. And when that happens, what you're looking at is the end behavior of the graph. So, and if you're looking at the end behavior as the horizontal problems that deal with horizontal asymptote, you're looking at some, okay, so let me define horizontal asymptote first, then it'll be easy to talk about it. So if the limit, if we take a limit as x goes to infinity, f of x is equal to L, and, or why am I writing and or both? Because it doesn't necessarily have to be same from both ends. It can be, because when you graph a function, certain functions do not have components on the both sides of the graph, possibly, okay? So that's why if at least one of them have, that will also work. So I'm taking the limit as x goes to negative infinity, f of x equal L. Then, you see I'm writing it as a line, y is equal to L is a horizontal asymptote. So this time, I'm not saying it's approaching to a point. Here, we were approaching to a certain point, L, sorry, certain number L. So this time, I'm not approaching to a point, I'm writing it as y is equal to L, which is an equation of a line. And in fact, this is a horizontal line. So that's what we call it, a horizontal asymptote. We'll get a finite number, y equals some finite number, which is L, but this is an equation of a line, so consider a horizontal line. Okay, so previously, for solving limit problems as x approaches infinity, positive or negative, we tried some algebraic technique. For example, we tried to divide the numerator and denominator by the highest variable, however highest degree, like x cubed or x squared, something like that. But this time, we are going to use a special rule called L'Hopital's rule. We'll discuss in more detail what that L'Hopital rule is. But before that, let's review non-zero over zero. So we solved a lot of problems that involve non-zero over zero cases. And whenever we have a non-zero over zero, right here, non-zero over zero cases, we know that we have a vertical asymptote. So the vertical asymptote can either be, we can have two answers, either positive infinity or negative infinity if it is one-sided. But if it is two-sided, then we need to make sure that it reaches to the same certain fixed number. Otherwise, the limit does not exist. Now, I'll quickly write down some example functions which we'll be using as we solve some of these problems related to L'Hopital's rule. As x approaches infinity, 3x minus x squared, we can see that if I plug in infinity, which we were not going to do, but we can see that this function x cubed is dominating here, so we're going to get negative infinity. And then if I am writing x as x approaches infinity for a function like e to the x, this function blows up to infinity, and we'll be using them as we solve problems. So I'm just quickly introducing them here. You can also think in terms of graphs as well. So now if we take this function arctangent, so how does the graph of arctangent function look like? So on the first quadrant it kind of goes in this way, and in the third quadrant it goes this way. So there's a height of pi over 2. If it goes to the positive infinity, we get pi over 2. And if the same function goes to negative infinity, or 10 of x, we get negative pi over 2. And also functions like this, where we have limit as x approaches 0 from the right side or positive side. For a function ln of x, we get negative infinity. And for when x approaches infinity, for the same function ln of x, we get positive infinity. And let's take another one. As x approaches 0, the function x squared, 1 over x squared, is a vertical asymptote because it's non-zero over 0. So we're going to get a positive infinity. Okay. So we'll be using them as we solve more problems, and we'll also see graphically. Now, what does indeterminate form mean? So let's try to find that out. So let me write it first. So the limit in this form does not tell us what the limit is approaching. What does that mean? So in this form, we literally do not know, just by looking at the function or some direct substitution, what would be the value of that limit. So let's take a look at some examples quickly. So if I have a function limit, if I take limit as x approaches infinity, 3 over x squared, and if I do the direct substitution here, I can see it's going to be 3 over infinity. So I know for sure that a constant over some infinity is 0. So this is not indeterminate. So this is not indeterminate because we have already determined the result, which is 0. Now let's take a look at another example. Let's say limit as x approaches 3 plus, which means from the positive direction, and the function is x over x minus 3, and if we do the direct substitution, what we can get is 3 over 0. Now, the 3 over 0 is essentially constant over 0, and that we can write as infinity. So again, this is not indeterminate. If we take a look at another example, for example, limit as x approaches 0, sine of x over 1 plus cosine of x. And again, if I do the direct substitution, this is going to be, so sine 0 is 0, cos 0, that gives you 1, so we get 2. And we know that 0 over 2 is 0, so not indeterminate. Okay, so we are familiar with all of these. We have seen functions like that. We have evaluated functions like that. We've taken limits of those. These are nothing new because we can determine this. We have determined them before. But now we want to see what are some of those functions that gives us an indeterminate form that we cannot immediately solve. So these are the indeterminate forms. So 0 over 0, 0 times infinity, and infinity minus infinity, and the 1 to the infinity, 0 to the 0, and infinity to the 0. These are all indeterminate forms. If we have a function and we do the direct substitution and see that any of these forms appear, we're not going to be able to solve immediately according to our current knowledge, although algebraically we can try by dividing by the highest exponent. There's a process, but we're going to learn a new method, which is L'Hopital's rule. I'll discuss at length how to solve that with L'Hopital's rule, but I want you to recognize what these forms are, so that if you can see when you're solving a limit problem, if you can recognize any of these forms, you should be able to say, okay, this is an indeterminate form. Do you have a question? Yes, so 0 times infinity, we don't know if it is going to be infinity, if it is going to be, it's not going to be 0 times infinity is not 0, okay? So if the infinity is really large, and infinity is not a fixed number, okay? So 0 times infinity can be positive infinity, can be negative infinity. It is indeterminate. We are not going to be able to directly say what the limit would be. We're not dealing with numbers here, okay? These are forms. 0 times infinity is infinity over infinity. These are certain forms and types. We're not dealing with 2 integer numbers, okay? So if we can recognize these forms, our goal is to find out the limit. So once we have these indeterminate forms, we're going to be able to find limits. We'll be using L'Hopital's rule or some algebraic technique. Does it make sense? Okay, good question. Now, there's something I'd like to mention, that if we have something like this, in negative infinity over infinity, or I don't know, so it's infinity over negative infinity, all of these, we're going to label them as infinity over infinity form, which is essentially a type, okay? So if you see negative infinity over infinity or infinity over negative infinity, as soon as you can recognize that, you know it's one of the indeterminate forms, which I want to categorize them or label them as type infinity over infinity, okay? So we don't make a distinction whether it's positive infinity or negative infinity when it comes to recognize this sort of forms. Okay, so let's take a quick look at how they look like in an actual problem. If we take a limit as x goes to infinity, x squared plus 1, 3x squared plus 2, and now if I do the direct substitution, what do I get? So plug in infinity, I mean we're not going to do that in reality, but it's going to give us infinity over infinity form. Let's write explicitly form. Okay, so this alone could go to positive infinity, negative infinity, or any finite number. Okay, so we don't know where exactly this is going to be. So this can go to any positive infinity. Let me write it down. It can go to positive infinity, negative infinity, or any finite number. Okay, so this is why we call them indeterminate form. So these are the indeterminate forms, okay? Now to solve problems where we can recognize indeterminate forms, we're going to use a new technique called L'Hopital's rule. So L'Hopital's rule, this is named after a French mathematician, L'Hopital, but the interesting story about this is that L'Hopital actually did not invent this. So there's a Swiss mathematician, his name is Bernoulli. So Bernoulli was working under L'Hopital. So Bernoulli was the Bernoulli originally discovered it, but L'Hopital published it in his book, and since then it's widely recognized as L'Hopital's rule. But the original discoverer is Bernoulli, and Bernoulli, after L'Hopital's death, claimed the authorship. So be a mathematician and claim the authorship. Be smart. So let's try to understand what does the rule say. If we have this limit as x approaches 0, a function at the top and a function at the bottom, and then after plugging in the limit value, if we see, we can recognize either 0 over 0 or infinity over infinity, this form, which we learned that these are indeterminate forms. If we have any one of these forms, only then we can apply L'Hopital's rule. As long as we can find this form, we'll continue to apply L'Hopital's rule. Does that make sense? We'll see that with an example, but let me write down what the rule is, okay? So, we take the limit as x approaches a. We take the derivative of f of x and the derivative of g of x. Okay. So L'Hopital's rule is absolutely simple. As you can see, all we're doing is taking the derivative of the top function and separately taking the derivative of the bottom function. Don't apply quotient rule just because it's in the quotient form or single fractional form. This is L'Hopital's rule because we have 0 over 0 form or infinity over infinity form. So it's not the quotient rule. This is L'Hopital's rule. Take the derivative. Okay. So let's try the first example, and we're going to start off by applying, by doing the direct substitution. So if we plug in x equals 0, so we're going to get 0 over 0 form. Okay. So we know that from the indeterminate forms, list of indeterminate forms, we learned that this is a 0 over 0 form, which is an indeterminate form, and which also satisfies the condition for L'Hopital's rule. We have 0 over 0 here, okay? So I can apply L'Hopital's rule. In short, I'm writing LHR maybe, yeah. You don't have to write it. I mean, I'm just writing it just to distinguish the fact that this is where I'm doing calculus, this is where I'm doing algebra. So in this line, I'm going to be applying this L'Hopital's rule, which is a calculus. So if I take the derivative of x, what do I get? 1. If I take the derivative of the bottom function, e to the 4x, I'm going to get 4e to the 4x. That 1 disappears, so this is what I get. Now, let's check. I missed the limit, I guess, so I need to write the limit again. So let me write down the limit. I have to continue to write the limit as long as I'm applying this L'Hopital's rule, okay? Okay. So if I now do the direct substitution, what do I get? I get something like 1 over e to the 0 is 1, so I'm getting 1 over 4. So the limit for this function as we evaluate it is going to be 1 over 4. Okay? So we have learned what are the indeterminate forms and how to recognize these indeterminate forms and how to solve problems involving indeterminate forms by using L'Hopital's rule. And the L'Hopital's rule is that if you have 0 over 0 or infinity over infinity form or type, then you can take the derivative of the top function, separately the bottom function, and then evaluate as long as you see that we don't have any indeterminate forms. Okay, so with that, I'd love you to solve this one, example number 2, and I'll set you free and we'll be walking around to help you out. Okay.
How you guys doing? The L'Hopital's rule, you're right, because there's no question was on you just taking the derivative of the top and taking the derivative of the bottom.
Is it going negative infinity? Is that what it is?
It's not going to negative infinity. You want to do it one time. What do you have? You'll have x to the 98 and x to the 99. Okay? Do algebra with the punchline here is do algebra with that. Because otherwise you're going to have to take like 98 or let's call it. Doing okay?
Yeah. Am I in the right direction?
Yes. Okay. And sometimes you do have to use L'Hopital's rule once. Okay. Sometimes you have it in 0 over 0 and infinity over infinity. We're going to have to use L'Hopital's. Okay. But we said, otherwise we have to do it 98 times. Do your algebra for you. Okay. Clean that up. Either way you want to look at it, 99 over 50. Alright, so 99 yeah, that's going to go up.
Okay, I think many of you already solved it. Many of you got stuck with some algebra, but you at least didn't get stuck with the calculus. So algebra is something you can work it out on your own, but you've done a good job so far. Many of you already solved it. Great, that means you learn how to apply L'Hopital's rule, which is essentially just taking a derivative, nothing more. I'll just show you quickly how to do it so you can check with your answers. So let's see if it is, what form it is. Okay. Okay, so just a second. Okay, so if we do the direct substitution, what we get is infinity over infinity form, okay? Now, since it's infinity over infinity, we're allowed to use L'Hopital's rule, which is legal. Now, let's write the limit as x approaches infinity, and all I'm going to do is just take the derivative of the top function. If I take the derivative, it's going to be 99x to the 98. And the bottom function, after taking derivative, it will be 100x to the 99. Okay, so now we can simplify it a little more. I mean, I can write it as limit as x approaches infinity. I can write 99 over 100 x. Now, if I evaluate it, I mean, check what form it is, we plug in infinity, we're going to get 99 over some infinity. And a constant over some infinity gives us a 0, so I'm going to write that it's 0, so that is the answer. That's the limit of this function. So we only have to apply L'Hopital's rule once, not twice in this case. But let's look at this problem. Many of you said that you have to apply twice, probably because you didn't simplify the algebra. So you know that simplification helps. Algebra is important. So now let's try this one. Let's see. If I plug in 0, what do we get? So we have, okay, so we're going to get 0 over 0 form, because sine 0, 0, cos 0, 1, that gives you 0 over 0 form. And if we get this, what do? We're going to apply L'Hopital's rule. I'm just going to simply write L at the top. You don't have to write any of those, though. So if we apply L'Hopital's rule now, what do we do? We just take the derivative, no big deal. Just take the derivative and you've learned how to take the derivative. So we take the derivative, and this is going to be 7 minus 7 cos 7x over sine of x. Now this is important. Are you going to just evaluate and say we found the answer? No, because as long as we find indeterminate form, we will continue to apply L'Hopital's rule. Okay, listen to me again. As long as we find indeterminate form, we will continue to apply L'Hopital's rule. It can be 3 times, 5 times, 10 times, doesn't matter, 100 times. If the indeterminate form shows up, we're going to continue to apply. So let's see if we still have an indeterminate form. So don't just stop after applying L'Hopital's rule for the first time and think that we found the answer. No, that's not probably going to happen, but it might. In the simplest example, it might or it might not. So, let's try this one, cos 0 and sine 0. So this is also giving me 0 over 0 form, which means I'm going to take the derivative of the top function and bottom function all over again. So I'll continue to write the limit as x approaches 0. And then if I take this derivative, we are going to get 49 sine of 7x over cosine of x. Okay, so can we do the direct substitution again to see if another indeterminate form shows up? Okay, so we do the direct substitution, cosine of sine of 0, and we get a 0 at the top, and at the bottom I get 1. So is this an indeterminate form? 0 over 1. Can anyone tell me quickly, is this an indeterminate form? No? Right. So this is not an indeterminate form. I'll just cancel it out, and I'm not going to apply L'Hopital's rule anymore. I can now just evaluate the function. Okay? So this is 0 over 1, and 0 over some constant is 0. So that is the answer. That is the answer. That is the limit of this function. So we evaluated, and in this case, we had to apply L'Hopital's rule how many times? Twice? Okay, good. So, any questions so far about L'Hopital's rule? Do you understand L'Hopital's rule? Any questions or comments? Okay, so but feel free to ask questions anytime. Now, this function is a little bit interesting because, as you can see, this is a composite function, right? This is a composite function. It has a function, inside function and outside function, right? Inner function, outer function, however you call it. So, we can work on this in two parts. First of all, let's focus on inside function, okay? So, to solve this, which one is the inside function? Let me say that this is the inside function, okay? We're going to work on this one. So let's let L is equal to limit as x approaches negative infinity. And what is my inside function? X squared plus 4 over 4x minus 1. This is my inside function. I've just written the limit that is already given, and the inside function, and we let that to be equal to L. Okay, just labeling, and it will be useful and simple because I labeled it. We'll see why this labeling is useful. Okay, so what do we do next? We check what form it is. Is it indeterminate or not an indeterminate form? By direct substitution. So if I substitute negative infinity in this, what I'm going to get is infinity over negative infinity. Okay? Does it make sense? If I 4 times negative infinity minus 1 is negative infinity. So, what form is this? This is infinity over negative infinity. It doesn't matter because I said that we are just categorizing them as a type. And what type it is? Infinity over infinity form of the indeterminate forms, right? So this is an indeterminate form, which means I am allowed to apply L'Hopital's rule. So let's apply L'Hopital's rule. And what that means is that I'm going to just take the derivative of the top function and the bottom function separately. So then taking the derivative of the top function gives me 2x, taking the derivative of the bottom function gives me 4. So am I done yet? No. I have to see what form it is. So if I do the direct substitution again, it's negative infinity over 4. So is it an indeterminate form? It's no longer an indeterminate form, which means we can find some value, some limit, right? It's going to approach to some limit. So now what we're getting here is negative infinity over 4. What that means is if we have negative infinity or infinity over some constant, that's going to be equal to infinity, but in this case it's negative infinity. And that is equal to L, okay? So L is equal to negative infinity, which means the limit for the inner function is negative infinity. Okay. Now, we understand the end behavior of the inner function. So the inner function is approaching to the negative infinity. That's our analysis, our comment about the inner function. Now let's look at the outer function. Or outside function, whatever. So, to evaluate the outer function, I'm going to say let u is equal to the inner function, which is x squared plus 4 over 4x minus 1. Okay, so I've just labeled the inner function, and that labeling has some usefulness. I'll show you what that is, but as you can see, arc10. Okay, so I've written arc10 of u with some labeling, just calling it a different name, nothing significantly different, okay? But why am I doing that? Because see, since we figured out what the limit for the inner function is, we're going to, that means we understand the behavior of the inner function. And we're going to take into account when we're evaluating the outer function. So, the limit for the inner function is negative infinity. So, what color can I use? Okay, I don't know, red. This is super duper important. I'm going to give the highlights. Okay, this is super duper important. This is not the same limit as it was given, which was infinity, okay? This is not the same limit. The limit that I'm using now is the one that I have found after evaluating the inner function, okay? So, since my limit for inner function has, after evaluation, the inner function has changed, I need to update that, use that in my outer function. So, what did we get for our L? What is L? Negative infinity, right? So I'm going to write negative infinity here. And then arc 10 u. Okay? Now we can evaluate it. Now we can evaluate arc 10 function. And we can evaluate it at negative infinity. So if I evaluate it, we have found out previously, I've written a list of things about a bunch of example functions. Let's go back and see them. So now you can see what is the behavior of the arc10. Okay, so the arctan is when evaluated at, oops. So when evaluated at infinity, we get pi over 2. When evaluated at negative infinity, we get negative pi over 2, okay? So now I can use it. Now I can use that. Let's use that now. Okay. So so let's use this arctan here. So the arctan, if you evaluate it, we're going to get negative infinity over 2. And if you see it graphically, this is how it looks like. Here it goes something like this. And here you have negative pi over 2. Here you have positive pi over 2. So you can see my new limit after the evaluation is negative infinity, which means it's going to this direction, negative pi over 2. Does this make sense? How we're going to evaluate composite functions. Does it make sense? Any questions on that? There's some labeling which you could solve without labeling as well, but then you'll make mistakes. So remember to label them correctly, but make sure to use the limit from the inner function to the outer function. So the limit we found after evaluating the inner function, that's the limit we'll be using. Although in this case, it looks the same, but if we would have found like positive infinity after evaluating the inner function, then my result would be on the other direction, like in this direction at that time, right? So then my result would have been different, like pi over 2 instead of negative pi over 2. Okay, so now I'd love you to solve example 5 in 30 seconds. It's super duper easy. Can you solve it in 30 seconds? And raise your hand as high as you can if you are done with it. Okay, tell me, what's your answer? A lot of you have already solved. Okay, what's the answer? Huh? 4? Okay, who said 7/5? 7 over 5. Okay, so what did you do? You just applied the direct substitution, right? So if you apply direct substitution, and if you don't get any indeterminate forms, what does that mean? Do we have to apply L'Hopital's rule? No, so it is just going to be 7 over 5. Through direct substitution, no fancy rules, nothing is required. Okay. So, we learned L'Hopital's rule, we know the indeterminate forms. So, we have also seen indeterminate forms like the 0 times infinity or infinity minus infinity, right? What do we do if we recognize forms like that? I mean, if you write this one, what do we get? 0, if we substitute 0, that coming from the positive direction, we are going to get 0 times negative infinity, okay? Which is 0 times infinity form, right? Negative doesn't matter in this case. We're dealing with the type, categorizing them as a certain category or type or form. Okay, so what do? We figured out, we recognize an indeterminate form. Are we just going to yell L'Hopital and apply and start differentiating? Is this what we're going to do? He says yes. Okay, super excited about L'Hopital's rule, right? Okay, but that's not what we're going to do. That's not what we're going to do. Let me tell you why. Let's revisit our L'Hopital's rule. What is this L'Hopital's rule? Oh my god. Okay. So where is this rule? This is L'Hopital's rule, right? So, okay, let's read the statement of L'Hopital's rule again. We can see that L'Hopital's rule clearly says we can apply L'Hopital's rule under a certain condition, that is infinity over infinity or 0 over 0. So the other indeterminate form that we found, let's say 0 times infinity, or any other indeterminate form we've seen so far, infinity minus infinity, even if you find those indeterminate forms according to this L'Hopital rule, you're not allowed to directly apply L'Hopital's rule. Does this make sense? I want to emphasize on this a little bit because this is where, people get excited and yell, yeah, L'Hopital and apply, right? We're not going to do that. That's not allowed. So, as long as we cannot find infinity over infinity or 0 over 0 form, we cannot apply L'Hopital's rule. But here's the trick. Since we have recognized that it is one of those indeterminate forms listed, what we can do is we can manipulate the algebra a little bit to make it look like infinity over infinity form. Does this make sense? It's not letting me, the function crashed. Okay, so we're back. Does this make sense? We can do some clever algebra to manipulate the function to bring infinity over infinity form, and that's what we will try to do. And it's easy to do it with some clever tricks. So I can write this as, so I have ln x at the top, and at the bottom I can write x to the minus 4. Does that allow me to write it as infinity over infinity form? I mean, first of all, tell me if it is algebraically valid, if I can do it. Can I do that? I can bring the x to the 4 in the denominator with a negative power, x to the negative 4, right? I can do that, right? That's allowed. So if we have that, what do? We can take the direct substitution, and with that I can see I have a negative infinity over infinity form, okay? So which means I can apply L'Hopital's rule. Does this make sense? We did some clever algebra to bring one indeterminate form into another indeterminate form, which is the form we need to apply L'Hopital's rule, which is 0 over 0 or infinity over infinity. So now, can you apply L'Hopital's rule on your own? Just take the derivative. Can you take the derivative? Yeah, we can walk around or help out, but we don't have much time though. Okay, so we'll walk around and help you out, but take the derivative and just solve it. Okay, we can walk around and help you out. Okay, so if we take the derivative, this is how it looks like. So we take the derivative, ln of x is going to be 1 over x, and x to the negative 4 going to be negative 4x to the negative 5, and we can just simplify the algebra a little bit, just a little bit. So then it's going to be x to the 4 over negative 4, and then if we evaluate it, what do we get? We get 0 and negative 4 at the bottom, which means 0 times negative 4 is 0, and that is the answer. All right, everyone, thank you so much. Have a great weekend. See you next week. Take care.
Oh, okay. You're actually just different people. Yeah.